Welcome everyone, and welcome to this session of the Information Universe mini-conference. In this session, we will be introduced to two target field lab projects about the future of visualization with Horus and Open Space. We will conclude this session with a book announcement, Powers of Two by Edwin Valentijn. For the first part, we have two different speakers with room for questions at the end. Please note the raise hand feature at the bottom of your screen. You may use this at the end of each talk to ask questions. You may also use the chat. With that, note that you can choose to send your messages to all attendees. We start with a collaboration of Target Field Lab with a local Groningen enterprise called Horus VR. And we have Bas Beukers with us, the CCO of Horus VR. He will talk about VR becoming reality during the new COVID-19 pandemic within the Target Field Lab project. Bas, the floor is yours.
Well, thank you, Marlies. So the upcoming 18 to 20 minutes, I will guide you through my virtual office. Before this, I would like to give you some explanation about this video, because it's not an ordinary video, it's the 360 video. But due to the limitations of this Zoom meeting, I made a recording of this, but afterwards you can share or you can rewatch the video if you would like to do this. Okay, so I will switch my screen and I will start the recording. And after the show, well, you can ask me questions as well. Okay, Marlies?
Go ahead.
There you go.
My name is Bas Beukers, the Chief Commercial Officer of Horus VR. And today I will explain a couple of use cases we built with our do-it-yourself VR ecosystem. But just to start, it's good to know that you're already inside the virtual experience. Actually, this is a 360 video. For example, if you look behind you, one of the colleagues is serving coffee. I just said, thank you so much. So this means during the presentation, you can look around and actually you're your own direction during this live stream. If you would like to look up, please do, feel free. If you'd like to look behind you, go ahead.
I think there's a technical problem. I don't see a stream.
Yes, I also think there is a problem.
You can't see my screen. Let me see. Okay, I will try it again. Sorry, guys. Can you see myself now?
Yes, we can see that.
Okay, I will restart the video. Sorry for this.
All right.
Hello, everybody. My name is Bas Beukers, the Chief Commercial Officer of Horus VR. And today I will explain a couple of use cases we built with our do-it-yourself VR ecosystem. But just to start, it's good to know that you're already inside the virtual experience. Actually, this is a 360 video. For example, if you look behind you, one of the colleagues is serving coffee. I just said, thank you so much. So this means during the presentation, you can look around and actually you're your own direction during this live stream. So if you'd like to look up, please do, feel free. If you'd like to look behind you, go ahead, it's up to you. But to follow my storyline, it's better to follow me here in the room. Okay, so my name is Bas, I already explained. I'm the Chief Commercial Officer, which means I'm responsible for business development and sales-related matters. My company, actually the company I work for, is called Horus VR. And what we do is where we are building a do-it-yourself VR ecosystem.
Bas, it looks like the image is still, and Anders has a tip. When you are sharing the window, you have to tick the share sound button.
Or record it, and the only thing we do, I'm
sorry for this. What do you say, Marlies?
So we have a tip. Maybe when you are sharing the window, you can tick the share sound button. It's
yes.
And the image of the video, it's also not moving.
That's a little bit odd. Oh, that's a little bit strange. Okay. Your screen sharing. Looks like this works. Please move this. You can't see my screen is moving?
No, it is a still image still.
But you can hear the sound.
I can hear some sound.
Actually, it's mm,
Anders said that you have to stop sharing. Have to stop sharing.
yeah. Okay, select a window that you would like to share.
And you tick the button share sound before you pick the window at the bottom.
At the bottom, share computer sound. Okay, this one. Yes? Let me check if it works, okay?
All right.
It has, actually it creates impact. So it must be a cost saver or a money
Okay.
generator. We have already a couple of showcases built on top of this platform, and it's good to know they're well accepted. To give you some background, over the last couple of years, we've won numerous awards with our services. One of the things we are very proud of is called Friend. Is this actually a little friend? I will explain later on what it does exactly. And with this service, we've won the 5G Innovation Award last year. This is a very prestigious award in the Netherlands, and the partners, for example, are KPN, Deutsche Telekom, Deloitte, Ericsson, and Huawei are the founding partners of this award. Just to explain something about our relationship we have with the University of Groningen and the Target Field Lab, because they invited me to tell me, to explain something about the platform we are building now. Is together with the Target Field Lab, we are building a do-it-yourself VR platform. And I explained we already have a sort of a platform, but we would like to make it an over-the-top platform. This means is you're not only able to set up your live streams and recordings, there are other platforms that can do the same. Think about YouTube, Facebook. So if you have a camera, you can set up the live stream immediately, and that's what it is. And at the end, you will have some problems with legal issues, content rights, intellectual property, etc., etc. And this was one of the things we saw, and we thought maybe it's a good idea to build our own do-it-yourself platform. So we started this project, I think, 1.5 years ago, and now we are in the actually almost in the final stage for this platform. This means we built a platform that enables you to upload your video. So if you have a live stream or a recording, you can log into our platform, store it over there, or if you would like to set up a live stream, you will go to your login page and then you can start your live stream. For example, I have a birthday party on October 1st, and I would like to start the stream at 12 o'clock in the afternoon. Normally, you have to hire a 360 production company to make this happen. And this makes it very expensive to set up your own VR experiences. But if you're able to set up live streams with a GoPro Max, and it's a consumer camera, 360, very easy in use, very user-friendly, and can do a lot what you can do with high-end cameras, for example, at the other side of the table. If you have your recording in place, then it would be nice if you can do some editing to make it more interactive or make it more professional. For example, that you can place in a title screen just to give the audience the information, okay, I'm now watching at the birthday party of Bas Beukers, October 1st, and at the end you would like to have, for example, an end screen. Just basic edit and clip functionality. But if you can make it more interactive by placing hotspots on top of the video, then it becomes more interactive and more immersive. People love to play with hotspots and make a vote, find, for example, the yellow balloon inside the room and click on it. So these little Easter eggs or gaming elements will make your video more interactive and more nice. So that's the creating stuff. If you go to the publishing side, then it would be nice if your video is available for people all over the world. This means you need a store, actually a storage platform where you can place your video. From there, it goes via distribution and a publishing key. It goes directly to viewers. So it's very important that people at the end can see what you have produced. Because yeah, if you have a nice video but nobody can watch it or can't use it, then well, then it's not a good idea. So, but it's a good idea when you can monetize these videos. For example, okay, my birthday party is maybe not a good example, but if you have a nice music festival and people want to go to the music festival and then they have to buy a virtual ticket. So there's always, actually it's very important that you also think about this business model. And this is the things we will support with our new platform. So if you have the technology in place, then you can think about use cases and showcases. Because we think a platform is just an enabler for people to create their own VR content. But what's the issue, actually what's the challenge to create VR content? And from there we have actually a very simple innovation workflow. Just to give you an example, this is a workflow we work with. It's called issue, idea, impact. It always starts with an issue. What's the issue from a client? Why does he need to stream live a funeral, a music festival, a sports game, or whatever? If you know the question behind this, then you can come up with an idea. So the technology we already have in place, so we have the do-it-yourself VR ecosystem. On top of this, we can create a creative idea. This means I have a music festival. I would like to give the audience all over the world a virtual front row main stage experience. So it looks like there are people that are watching the music festival at home. They can stand on, well, main stage and see what it looks like from a lead singer perspective. So then you see a full stadium in front of you and you're just sitting at home at your own couch. Very important, a business model, because even when it's not expensive anymore to create VR live streams, you still have efforts to make. So you need somebody who goes to the place, has equipment, all the things make it still a cost. So if you come up with a business model, then you will have a big idea, and a big idea creates big impact. Very simple. So every use case we think of, or actually every showcase we're thinking of, needs to pass this thing. Is it not a big idea because there's no business model, then it's not a good idea, and then we'll stop development. If it's a good idea, then we can create impact. Just to give you one example, is that we built a do-it-yourself VR low latency streaming platform. And that's a lot of technology, but what it does at the end is bringing this little girl inside the hospital back home to her own bedroom via VR low latency streaming. What it does, it's a sort of a Skype VR session. She can watch her father telling her a bedroom story from her own bedroom. And the reason why, because she's afraid, she's inside the hospital, and she had some difficulties to fall asleep during the evening, because she's not in her own bedroom. It's a large bed, it's a strange environment, but if you use an Oculus VR device like this, she's totally immersed by the experience, and she has the feeling that she's at home in her own bedroom. And that makes it a lot more immersive than an ordinary video stream, for example, like FaceTime or Skype. Because you're fully immersed, you can look up, you can look down, and after the first 30 seconds, you'll forget the environment, your real environment. So we did some research, and you see what happens is that the virtual reality, what they're in, becomes reality in just 30 seconds. And then she has the feeling, okay, I'm back home again. A very nice example. And this example of actually this use case is being used in 15 hospitals in the Netherlands already. And the first friends are being shipped to the UK, to Canada, to Belgium. So a lot of hospitals say, okay, this is something extra on top of the normal video streaming service we can supply. Just one example, but think about this is for patients' well-being, to increase the patient's well-being. But if you thought about bringing two colleagues together, they're not in the same room, not at the same office, and especially during COVID times, it's not common anymore that you will go to your office and to your own desk, but you stay at home and work from home. now you're able to collaborate in VR together. And this makes it a real immersive collaborative experience. And this is still the beginning, but we're getting there. To give you another example, is one of the friends we're talking about was placed inside a funeral home. There was a patient inside the burn center in Groningen, and he was not able to go to the funeral of one of his relatives. What they did, they took the camera, brought it to the funeral home, and put it on, and the patient inside the hospital was able to follow the funeral service from his own hospital bed. And this was a priceless experience for him, because he was thinking about, I have to miss this very important event in my life, and I'm just one of the family members that can't be there. But there are a lot of other reasons why you can't go to a funeral home. Because, for example, you're living abroad, or during the corona measures we are facing now, it's simply not allowed to place a lot of people inside the same room. So if you can place a virtual cam inside the funeral home, people from all over the world, who has access, of course, can watch the live stream. And afterwards, if they would like to, because of other time zones or whatever, they can still experience the funeral at home again. A very nice showcase, but the first question we got from Yarden, can you make it a scalable model? Is it possible that we can set up the live events ourselves and make the recordings ourselves? And then you can see the do-it-yourself platform we are building with the Rijksuniversiteit Groningen, University of Groningen, comes into place. We streamed, for example, to give you some numbers, we streamed over 600 funerals since the beginning of February in 2020. And the camera is just placed in 4 locations. Yarden has 27 locations in total. So we can, stream live, let's say, hundreds of funerals a month instead of the 600 in the last 6 months we already did. A very nice use case. People are well willing to pay for this. So it's also a healthy business model at the end as well. And this makes it a big idea. So the issue, very simple. People are not able to go to the funeral home and will miss the funeral service. The idea is we pick up the funeral service via virtual reality and stream this to the rest of the world. A very creative idea. Technical idea is we use the platform we are building with Target Field Lab. And the business model is that people at home have to pay for this. So they have to pay a virtual ticket. And that's been organized by Yarden. And it's a very common business model that people are paying for extra services. So this is a scalable model. The other thing is, this just one of the things we developed a couple of weeks ago, just before the summer, is that the entertainment industry has also some challenges in this time, that it's not allowed to, the same thing with the funeral homes. If you have a theater, you can hold up to 500 people, but you're not allowed to sell 500 tickets because you have to remain some distance between the seats. So this means if you have a 500-seat theater, you can hold up maybe 50 up to 75 people. But the costs are still the same. You still have to pay the artist and the crew around him, also security, the people behind the scenes, etc., etc. So if you can come up with an idea to sell virtual tickets, then you're all set. And this is what we call Theater 360. And Theater 360 is actually a virtual front row experience. This means we place a camera main stage, front row, or you can make a combination. So I would like to switch from front row to main stage, and you switch your own stream. There's also a possibility. But the main thing is that theaters are able to set up the live streams themselves. And this creates an extra business model for them. So the 500 seats was a limitation, and especially during the COVID pandemic, you have to go down to, let's say, 75 seats. But if you stream live, then you can sell, let's say, 100,000 tickets if you want to. Just to give you an example, we streamed live Mart Hillen. Mart Hillen is a famous guitar player in the Netherlands. And he has a huge fan base in the southern part of Europe, so in Italy and Spain. And that's because the way he's playing a classical guitar. But normally people have to, well, to buy a ticket, come from Spain to a local theater, and that's not what's happening, of course. So we streamed live Mart Hillen, and people from Italy or Spain can buy a virtual ticket. Actually, it doesn't matter if you're in Spain or in Asse. This is where the theater was placed. And they can watch the show. So from a local theater, you will become an international an international platform where people can perform and stream to the rest of the world. And this actually worked pretty fine. So we did some research. Are people willing to pay for an experience like this? Yes, they are. That's the good news. So normally you would pay, for example, in this case, you had to pay 20 euros to be a part of the show. But if you buy a virtual ticket, it goes down to 7.50 for the live stream. And if you would like to have the recording at the end, then you have to pay 5 euros extra. And that's not a problem for people at all. So people are well willing to pay a decent price for a virtual experience. And actually that's very good news, because then it becomes a business model for your theater. So it's not only a creative thing, a virtual front row experience, based on top of the platform we built with the Target Field Lab, but it also has a business model. And then you see things come in place, and then you create impact. So this is what we, what VR is standing for. We would like to enable people to benefit from VR technology. So we have numerous showcases, but for today, I would like to stay with these 3 cases. It's just a friend bringing hospitalized patients back home, even when they're not able to, a funeral services, and send a broadcast via virtual reality to the rest of the world, and also a front row experience called Theater 360. So if you have any questions or any ideas, we can build on top of the platform we're working on now. Feel free to ask some questions or to drop me an email. I'm more than well willing to give you an answer. Okay, that's it for today. Thank you for your time, and hope to see you in the near future. Okay.
Bye-bye. Hello, everybody. My name is Bas.
There you go. So just to give you an explanation, now I was the director and guided you through the video. If you start after this conference, the YouTube link, you can look around yourself. So just with a mouse click, you can look around, or you can even play it on an Oculus Go if you would like to go there. So actually it's a 360 video, and you can become your own director. That's what it is.
Thank you so much, Bas, for this very nice talk. It is definitely the right time to develop these kind of techniques. Let's see if there are any questions. If you have a question, then please see the button raise hand at the bottom of the screen, and you can raise your hand and I will give you the word. So let's see if any attendees have any questions. Maybe I can start with one question. What would you need as a person at home to view this experience? I mean, do you have enough with the screen, or do you think maybe in the future you want to add some special cameras?
Well, actually, to capture 360 imagery, you need a special camera. But what you see now is the high-end cameras that become now more affordable. It becomes more a consumer product. For example, GoPro came up with a 360 camera 1.5 years ago. And it's affordable for people, so they can make their own recordings. And that's already the good news. And but you still need a platform in the middle. So the platform in the middle, so you can use YouTube or FaceTime to create your own VR event. But then you're still facing some delays and latency in the video stream. To give you an example, for the friend solution, we had to build our own peer-to-peer communication platform. Otherwise, you will face a delay of over 30 seconds. So if you ask me a question expecting an answer, then it takes over 45 seconds, and then, yeah, there is no communication possible. So therefore, you need a special platform. And at the end, of course, the playback, then you can use a VR device. And this can be an Oculus Go, an Oculus Quest, or any VR device that's out there in the market. But you can also use, for example, a desktop computer. And the only thing you need to do is by moving your mouse, you can look around. It's still not the best experience. It's not as immersive if you use an Oculus Go, for example, but it works fine. Yeah.
All right, good to know. Thank you. I see one attendee with a question as well. Luis, would you like to ask your question?
Yeah, I can just unmute myself. I really wanted to make a point, actually, that I've seen that video in the original format when you're playing it interactively. And
yeah.
Of course, it's very difficult for Bas to show that feature. So I put the link to the video inside chat, and I urge everybody to have a little play with it, because it's really quite nice how you can initially start, looking at Bas, and then you can turn around and just sort of, look around the room, look at the ceiling, look at your feet. It's worth having a play.
Yeah, thanks for this, Reese. Yeah, I think that's that's the whole idea. So you can look around, and you are the director actually in this film. So if you think, okay, Bas is not interesting anymore, just look around, and look up, look down, and yeah, you can play along with it.
That's a very nice suggestion, and thank you also, Reese. And I see no further questions. So thank you again, Bas, for this inspiration.
Sure. Yeah.
And then we will go to our next speaker. We will go to a second Target Field Lab project with Open Space, open source software to visualize the universe with interactive research data. And the University of Groningen and Target Field Lab also work with the Open Space project in cooperation with the Hayden Planetarium in New York and the University of Norrköping in Sweden. And our speaker about open space will be Carter Emmart. He is Director of Astrovisualization at the American Museum of Natural History in New York City. To Carter, to keep an eye on the time, I will give you a notice when you have 5 minutes left. We started a little bit later, I will take that into account. And I will first give the word to Professor Anders Ynnerman to give an introduction.
Is Anders there?
Is Anders there? Let's see, Reese, do you see Anders? Oh, there we are.
Okay.
All right.
Okay, now I cannot hear you, but that's a different thing though. Let's see.
I can hear you, Anders.
Okay, now we're probably on. You did not promote me, I guess. All right, great. Thank you very much. It's an honor to be here. It's an honor to be the person to introduce my dear friend Carter Emmart. Now, Carter is the director of astrovisualization at the Hayden Planetarium in New York and at the American Museum of Natural History. And Carter has an extremely long list of achievements, and I will try to highlight some of the things from my own perspective of his amazing career. He really has an undergraduate degree in geophysics from the University of Colorado. And as many of you know, he has since then been involved in a large number of visualization and technical illustration work in space exploration and in astronomy. He has worked at NASA Ames, he has worked at the National Center for Atmospheric Research, NCAR, before he was joining AMNH. Now, he's also very well known for his directorship of a large number of space shows coming out of AMNH and the Hayden Planetarium, including some amazing shows like Journey to the Stars, Passport to the Universe, and the most recent one, Worlds Beyond Earth, which has an enormous impact in the planetarium community. He is certainly one of the pioneers in astrovisualization in combination with public outreach. And in view of this, he was honored with an honorary PhD degree from the University of Linköping in 2006. And also in 2016, he received the most prestigious award in the planetarium community, the Technology and Innovation Award. I met Carter for the first time in 2001 at the SIGGRAPH conference in Los Angeles. And at that point, we started to chat about the possibility to not only produce movies and videos of space and for science communication, but also to interactively visualize a large range of astronomical content and do that in a consistent way. Do it in a sort of a browser of the universe way. And this discussion was the beginning of a very long and still ongoing collaboration that has led to a large number of student exchange projects, meetings, also to the software UniView that some of you may have seen in planetariums all over the world. But in 2015, we also initiated the work on what we wanted to be an open source project to further distribute and reach the impact beyond the planetarium with interactive visualization in the astronomy domain. This project has now turned into one of the most advanced, or perhaps the most advanced, astrovisualization software package in the world. And the development is still ongoing with support from NASA and a large number of partners all over the world. So I am very pleased to welcome Carter to give his talk. And his talk is entitled Evolution of Planetarium Theaters, from Sky Demonstrations to Immersive 3D Science Description and Investigation. Thank you, Carter.
Thank you, Anders. Well, it's an honor to be speaking to you all today, and to be introduced by my good friend Anders, and also the range of topics and astronomical content here, Eric and Wendy. Wow, fantastic thoughts. So to talk about open space, what I'd like to do is I'm going to share my screen and just take us through a few things. I really want to sort of focus on open space and what that entails and where it's going, but leave room for some questions. So I have a lot to cover, so I'm going to share my overall screen here, and pardon if it seems a little messy. So I hail from the Rose Center for Earth and Space. We're if you're old enough, you may remember the old Hayden Planetarium and what that looked like, and it was replaced as a Millennium Project with the new Hayden Planetarium inside the sphere, in the upper portion of the sphere at the Museum of Natural History, and we have the various exhibits showing the scale of the universe, and in the center portion here is a timeline of the universe. The lower portion of the sphere is Big Bang recreation. We used the visualization from UniView, which Anders mentioned some years back, featuring our digital universe. I wanted to talk about this first. This digital universe concept came about through the rebuild of the old Hayden Planetarium to the new. And our illustrious director, Neil deGrasse Tyson, liked to frame it in a nice way. I still like to quote this, is that what would the planetarium of the 21st century be? Of course, the planetarium in its projection form was developed by Zeiss, and I'll just go to this image here. This is an image of the old Zeiss Mark I projector built in Jena, Germany, and projecting. To be quite honest, from this figure, I'm not exactly sure which city it's in. But typically you see the audience highlighted, but you can see the constellation of Orion in the sky, and you can also see a kind of hallmark of planetariums in this beginning in the first planetarium that was built in Jena, Germany in 1926. 3 years earlier, it had been sort of a demonstration on the top of the Zeiss factory in Jena. And but planetariums evolved, and every city had to have one. The first one in America was in Chicago at the Adler Planetarium in 1930. In 1935, the Hayden Planetarium opened up in New York, and typically they had a skyline that our original one. I understand there's still pieces of it out in warehouse in Brooklyn, which I have not seen, but parts of this original cutout of metal to create the New York skyline. And but the fantastical diurnal motions of the night sky, and also independent projectors for the planets and sun and moon, accompanied this mechanical, optical tribute, in a way, to the Industrial Revolution. And in ways that this strange creature in the middle of the room was always kind of a feature of going to the planetarium. And for the imagination, certainly of children, we had the Zeiss Mark VI when I started taking classes at the Hayden when I was 10 years old. But the motions along this major axis of the sort of dumbbell shape mimics that of the sky, and is very similar to an equatorially mounted telescope. Presentation mode here, I'm sorry that I was going to show a few more slides, but suffice to say that at this time, the Industrial Revolution, making the ability to have bigger and bigger telescopes, and then finally these optical mechanical devices in the early 20th century, led to...
Can I ask you a question, Carter? Can you also make the screen larger so that it fills the screen? My
apologies on that. Also, my ability to just, I thought this presentation would work, and as in Dropbox, it's not. I just wanted to really sort of make this point about these optical mechanical devices and telescopes, and the mechanization, essentially, of astronomy, and then the presentation of astronomy to the public was fantastic. This educational device was so popular that sort of all cities around the world began to develop these, and not just the Zeiss machines. Goto in Japan started making them. The Spitz company in the United States started making their versions. So there were different types of these, and they presented an accurate data visualization of the night sky. That depiction that you see in the background of Orion is accurate insofar as a sky map that was very accurately presented, and can be controlled for the diurnal motion of the night sky, the seasonal motion, and also the tilt of this axis of the central beast in the room could be adjusted to show the entire sky. In fact, one of the spheres we see here, the one facing us, is the northern sky, and the one in the background is the southern sky. So this has the ability to sort of project on a hemisphere, depending on its tilt, the entire 360 view of the night sky. So what was this, what was happening in technology, essentially, I'll just bring this smaller, I'm going to invoke another slide I had here, of what was happening in the technology areas of, I'll just try to make this a little bigger, is that in Neil deGrasse Tyson sort of phrases this question, but in the early 90s, the Museum of Natural History, before it committed to modernizing the Hayden Planetarium, it had modernized the dinosaur halls. And so in that, and the rethinking of the dinosaurs were actually hot-blooded and bird-like was a major difference. And so that renovation was enormous. And so the time it was seen, this trend in technology and immersive technology was really the trend of starting in the 1980s of the first digital planetariums, so the Evans and Sutherland company. But we teamed up here with our National Center for Supercomputing Applications that were doing, they had developed the Electronic Visualization Lab, part of the University of Illinois, had developed the CAVE, or Computer Assisted Virtual Environment. And what you see depicted on this image is actually something in the early 90s. It was very exciting, which was the linking up of multiple sites. Bob Patterson in the upper right is actually standing in the cave, and which you can just sort of see him in front of the screen. But then Donna Cox is over on the left, and below her is Stuart Levy. And this team of Donna, Bob, and Stuart had sort of created this technology, and they were also linked up to the Chesapeake Bay project, a number of these large visualization centers, all in the same data set. And so this is very exciting. And what could we do with this for astronomy, essentially? And they had worked with a number of astronomers. Let me just reduce this down. I'll get rid of this slide. And I'll talk about that later. So I'm just going to enlarge open space here and show you that we're now in this digital realm. So the big difference between the planetarium of our grandparents, let's say, was that ability to see the sky and all the attendant motions. We could certainly do that digitally, but we had gained a tremendous amount of information thanks to, again, the Industrial Revolution, larger telescopes, but also the computing revolution that completely made us immersed in data and an understanding of the universe more and more three-dimensionally. And so using three-dimensional data visualization to really show that. So here I show you the constellations, both in stick figures, the star-to-star connection. We see the zodiac. We see right here, I show Scorpius, and then we see Sagittarius, the Archer's arrow pointing toward the center of the Milky Way galaxy. This is a section of the Milky Way and that we can pan about. I'm in open space now. I'm going to pan around to something else that's in open space with us right now, and that's the International Space Station, and we're above the Earth. And so we're in this, and I'm going to move around the space station. And I have my controls. I thought about how I should present this today. Usually we present without the controls, but I'm just going to bring up my menus, and why not show you? So I'm centered on the ISS, going to pull around, but there's also a clock here, and the clock is not moving. So what I want to do is go to, I want to make sure that I go to let's go to 1 second per second. Let's go down. Oh, okay. Oops, let me just enter this. 1 second per second. I'm going to hit the, the start button, and you can see how slowly the International Space Station orbits the Earth. Slow, I'm making a joke really, because the International Space Station travels at 17,500, pardon me, miles per hour. I don't have my, I don't know what that is in kilometers off the top of my head, sorry. But anyway, it goes around the Earth in an hour and a half. You may have noticed as well that this image, this is amazing to me now, even that I can be on a Zoom call to you all, but at the same time that I am gathering the data of the Earth. This is an image of yesterday, and it goes down to 500-meter resolution, and we're approaching Portugal and Spain. If I zoom over here, there we see North Africa, and we can see Gibraltar and the Mediterranean. And also, you may notice that as far as the atmosphere, so this image is gathered. What we're doing is we're streaming data sets from, we don't want to hold all the data here, so we're actually using the web map streaming protocols to our colleagues at NASA Goddard and Goddard Space Flight Center and in Maryland. And so we're gathering this satellite data and displaying that. It's underneath an atmosphere, which is a physics-based atmosphere. The atmosphere is scary thin, according to the astronauts. Here we are, we're 400 kilometers off the Earth, and arguably where the sky goes to black in the trail off of the atmosphere above the Earth is about 30 kilometers or 20 miles. We're between Spain and France. What I love about this is that we don't see any borders. The borders are what we impose, but we could show borders and all that. I can fly in closer to Earth and fly around it like a Google Earth experience, but there's a lot of ground to cover. So I'm not going to waste any further time on this. I'm just going to bring up my my menu here. I'm just going to turn on the ISS Trail. And so then we're going to pull back away. I'm pulling my right mouse button toward me so it moves me out away from the Earth. And here we begin to see what I think of as this data display engine of open space is we have this complete interactivity, but we can show we were just moments ago at the space station. I could have told you all in gory detail about this, that, and the other part of the space station. But here we are, and we're looking at the orbit. And the orbit is, is 400 kilometers off the Earth. I mean, it's when we show this to audiences, I mean, people generally don't know how high the space station is. And so here we show that. I'm keeping the zodiacal constellations on. I'm zooming around the Earth pretty quickly. We actually come around, we can see the night lights on Earth as well. I could call up any particular day back to 2000 of this image of the Earth. This one in particular has no gaps. If we go back beyond about 2008, we see images that have gaps in it, but still we have this tremendous database to go through and look at Earth. And we can also look at many different spectral sensitivities and maps that are collected by the NASA Gibbs team. So let me move out here a little farther. I'm going to bring my menu back and just come up here and say satellites. Whoops. Let me just go back. Let me just do this. Focus, Milky Way, solar system. You can see we have many, many things here. Satellites. I want to turn on the geosynchronous satellites. When I do this, I'm going to speed up time here a little bit. So let's go to so I'm centered on the space station. That's going to make me zoom around. So I'm going to just focus on Earth here. And I'm just going to amplify time a little bit. As I do, I'll get rid of the menus again. And we can see that even under casual inspection, you can see how the space station goes around the Earth in an hour and a half. But the geosynchronous satellites out of 30,000 kilometers are going to go around the same rate of rotation of Earth. So they're going to hover above those spots. And in this case, we can illustrate that 30,000 kilometers is 1/10 the distance to the moon. So if I come out here, I'm going to now turn on trails. We saw trails of satellites, but now we see trails of the planets around the sun. And also we have the moon. Now the moon's orbit is a little dim, so let me come in here. And I'm gonna, where is, okay, so come down here, moon. And I'm gonna come down to moon trail. And I'll open that up. I'll get rid of some of these other things. And appearance. No. Transparency. Okay, whoops. Appearance. And let's just brighten that up. Okay, so now we see the moon. And that's fine. And then farther out, here's Orion in the sky. We saw that in the planetarium sky. And our zodiac. Now, what is the zodiac? Of course, the sun seems to move through these constellations as we go around the sun. So if I just bring this back up, my time, I'm going to go from seconds into hours, and I'll speed this up. So now we see as we, well, that's maybe a little fast. Okay, we'll bring this a little slower. And so now we see the satellites buzzing around the Earth once a day. We see the moon going around the Earth once a month or a month. And we can see as we go around the sun, we're centered on the Earth. The sun seems to go around the Earth in the sky. Well, of course, Ptolemy had a sophisticated interpretation of that. Everything went around the Earth, but Copernicus made a simpler interpretation of that, of us going around the sun. At this point, to move farther out into the data sets of the universe, what I'd like to do, I'm just going to center on the sun. So that's our center. And we can see now that the zodiac has nothing to do with the alignment of the Milky Way. And the Milky Way, if I was to level that and make that our new horizon, well, that would make sense if I start to pull away from the sun. Now, we've left on the zodiacal artwork as well as the constellations. I'm going to just move over to this location for a second. And we can see the Southern Cross, and we can see the brightest star in Centaurus here, Alpha Centauri, and we know is the nearest star to us. What I'm doing is setting up for essentially the jump beyond into this ability. We started out with Earth and an intimacy of detail at the International Space Station. But we are going through what open space has is called this dynamic scene graph that allows us to actually move through scale and do that accurately, and which is a tremendous thing. If I just was to come back for a moment, not all the way to the Earth, but just point out light travel time. If I say that Alpha Centauri is 4 light years away, well, the Sun is 8 minutes away in light travel time. Neptune is 4 hours away. And so if you think of, a 24-hour day, well, if the radius of Neptune's orbit is 4 hours or the diameter is 8 hours, you get 3 solar systems and put them together, that's 1 light day. And so now I'm going to move out. We'll brighten the sun so that now we see the sun the same brightness as the other stars. And as we do, if I move back and forth, you can see there's a sort of parallax of Alpha Centauri coming off the wallpaper of the stars, if you will. And then I'll pull back even farther. And that's 4 light years. You notice the artwork, we've sort of placed that at about 10 light years or so. And that we have the nearby stars. This is Sirius over on the right, and Procyon. So Sirius is about 10 light years away. Procyon is about 12. And some other stars over here, what we see, we have Vega, which is about 20 light years away up here, and 16 light years away, Altair. Over here, a yellowish star, Arcturus, and the star Murfred in the constellation Boötes. And so you get the point. We're out here in the sort of 3D space now of the constellations. If it's a little hard to see, let me just come up here and readjust that for us. Solar system, Milky Way. I'll go back to my constellations. And let me just increase their line width. Transparency, there we go. So we can now see the constellations as 3-dimensional sort of star-to-star connection. And we get out here and we have the Milky Way band, which is still, so what is the Milky Way? We thought they were sort of clouds, a silver road, the different cultures calling it different things, but some version of milk, a river. And it wasn't until Galileo, with the first telescope and making note of what he saw in telescopes, thus science, it said they're uncountable stars. And so that began this notion that, okay, these are stars beyond those that we can see with our naked eye. Well, how far out does that go? Well, how far out are we right now? So what I'd like to do is just come in here and I'm going to grab one other thing here is, let's see, close up some of this, open up here, and I got to turn on something, this concept of the radiosphere. How far away have our radio signals reached since the Earth became radio bright? How am I doing for time? Okay, I'm just looking at my time. So here we have a sphere which is oriented in that of oriented to that of the Earth. So this would be the North Celestial Pole and South Celestial Pole. But we've given this a radius of 80 light years. So this represents around the time 80 years ago when the Earth became became the brightest radio source, blasting other radio waves in the solar system. So any of the stars within here have heard from us. Anything beyond that this is expanding at the speed of light, but any stars beyond this have not heard from us yet. So in a sense of looking for ET out there, extraterrestrials. You might also wonder, well, we've also discovered stars that have systems of their own, the exoplanetary systems. I'll open up the Milky Way here. I'll come down and close up my constellations, but I'll come down here and turn on a couple things that I want to show. This digital universe concept was developed so that we would have three-dimensional data sets in which to really explore in the planetarium of the 21st century. And so our space show productions, the foundation is this digital universe. And when Anders and I started talking, we developed first UniView and then later Open Space, this desire to really show the universe in this way of all these three-dimensional data sets. Way beyond the constellations here, this is the unfamiliar sky. So let me just come down and close up a few things. I'll open up my exoplanet choices. I have two. These are the ones that have been found dynamically, and you can see a tremendous number of them are within our radio sphere, and even more beyond. We also have the Kepler the candidates that are out in one direction that shows that patch of sky where Kepler was staring, and found this plethora of exoplanets or candidates. My point in showing this is that we now think of stars as having planets. Revolution has taken place since the first one discovered in 1995. I'll turn those off. I just want to turn on, say, globular clusters. Globular clusters had a lot to do with our understanding of where we were in this Milky Way galaxy. There we see the Milky Way beyond the radiosphere. Lots of globular clusters off where the Milky Way is bright. Let's turn 180 degrees, no globular clusters. So there are various data sets that we can turn on. Let's see, I'll turn on OB associations. These are where bright stars are. And so here we see these particular bright star associations. These are all parts of this digital universe. Now, let's move out beyond this. Okay, so that's our portion of the galaxy. We are now starting to see a galaxy that's being revealed to us as I pull out farther, but in coordination, in context with all this other data. The globular star clusters are the pentagons, and then the bright star associations we see really just close to us in our part of the Milky Way galaxy. And so this volumetric model of the Milky Way that we see is not artwork. It's actually the result of a constrained simulation from our colleagues at the National Observatory in Japan. And Baba, Wada, and Saito are the authors of this. And we contacted them, worked with them as a data source for visualizing the Milky Way galaxy for our space shows. And we've taken that and we've given that over. Eric Sundin worked at Linshipping on actually putting this particular model in. And so this collaboration, open space is, I didn't even really introduce it properly, but open space is NASA supported. So it's open source, that's its name. But it's this collaboration with Linshipping University and Anders' team that extends back about 20 years. And but also the form of the NASA grant that we got has enabled us to also work with collaborators that Anders has been working with for years. The University of Utah, the Scientific Computing and Imaging Institute, as well as the New York University's Tandon School of Engineering. So our developers are at these 4 locations at AMNH, Linshipping University, in Utah, and New York University. And so that we make this freely available to the world. So beyond the Milky Way, what's out there? Let's go. I'm going to pull out just a far enough here with the Milky Way. Sometimes, let me see, Milky Way volume, I'll open that up. Sometimes the star component makes me stutter a little bit, but there's a lot of data in here. As we pull out, this is the Milky Way, our home, but our nearest companions essentially are the large and small Magellanic Clouds. The nearest big galaxy to us is Andromeda, and if I pull back far enough, I should be able to see Andromeda. I'm sorry if it's stuttering a little bit. That's because I have the names turned on. And we've now stepped out into the extragalactic realm. And we're moving exponentially, of course, as we pull out. I'm taking bigger and bigger steps, and it would take forever to get across the universe if I didn't. So as I pull back, we now see the local group, and we're immersed in Brent Tully's atlasing of the galaxies nearest to us out to a few 100 million light years. And so we're in the center, just as we lost the Earth and lost the sun, we're now losing the Milky Way galaxy immersed in these. And we see out here about 60 million light years away is the group of galaxies, about 1,000 strong, the biggest sort of downtown of galaxies near us, that aligns with way back home with the constellation Virgo. And but if I come in close, we'll see, yes, it's all data. These are all positions in 3D that we put in. There are about 30,000 galaxies in this. And if I pull back far enough, now these are nice because they surround us. But if I'm doing this transition now into the Sloan Digital Sky Survey, and I'm going to let this spin around just a little bit for us. You might wonder, that people always wonder, why is the universe shaped like a butterfly? It's like we talked about light years, he's talking too fast, and suddenly we're out here amongst all these galaxies. The dark areas align with our Milky Way galaxy. And so that makes it difficult for us to pick out all these very distant, very dim little galaxies. Also, this Sloan survey was from Apache Point, New Mexico in the Northern Hemisphere. So we have a Northern Hemisphere bias. And so in the Southern Hemisphere, we have other data sets that we could show, but I want to sort of pull out even farther. We see the large scale structure of the universe there. We also see something coming off to the bottom. I'll talk about that in a second. But if we pull out far enough, we're now going to see the quasar components of the Sloan survey. And so with them, we do not really have enough to really visibly see the large scale structures such as we see in closer. In other words, the galaxy clusters, superclusters, and voids, giving us this frothy nature of the galaxy distribution that we see. And then far enough, if I go far enough out into the quasars, well, we start to fade up the Planck view of the cosmic background radiation. Now, we're using a Hubble constant of about 70, and so this model out here now, we're out into look back time. I guess the radius of our CMB is out about 42 billion light years at that Hubble constant. Well, what is this line that is suddenly appearing? This was shared to us from our colleagues at the Space Telescope Science Institute. This is the Hubble Deep Field. And so an area that is sort of smaller than what we see visibly on the sky of like the full moon. But this reaches out, and I like to come around here like this, that this represents, of course, the sort of farthest we can see. In fact, if I pull out far enough, well, then we see our cosmic horizon in time, essentially, and how far out to where we can see. But if I pull inside here, then we can see that Hubble Deep Field, in fact, what I can do is just come up in my settings and come up in my, I'm going to widen my field of view for you all. And when I do, that should allow us to at least see that the Hubble Deep Field is sort of blowing past all the quasars and all that, as you would expect, because it's our deepest sounding of the universe. Now, what does this line mean? This means This is what we see with one survey, the Sloan survey. But of course, the Hubble Deep Field indicates that this is sort of what we'd see all around us, thus filling in. You know, if we could do a Hubble Deep Field everywhere, it would be tremendous. But this illustrates this view of this discretization has to do with actually a movie that was made for 3D by the Space Science I'm sorry, the Space Telescope Science Institute, our colleagues there. And so I'm going to just come on back down. Now this is a fairly designed to really focus on it says my internet connection is a little unstable. I hope you are all still hearing me. Okay. But OpenSpace was really designed to do show dynamic simulations. Also planetary data coming in very close. Maybe I'll just show you a little bit of that. Once again, I just look at my time here. I know that we're getting long, but let me just do the following for a second. I'd like to refocus on Mars, and just a slight deviation from where we were. And also, at this point, I'd love to just sort of take the time and turn off lots of things on the screen, but I'm going to leave them on, just in the sense of time. And come up on Mars, another world with an atmosphere. Notice how the data set, the global data set is loading. Oh, there's Valles Marineris, nicely showing that's the gaff across the screen that we see. And this is a global data set basically for color. And so what I want to do is just come up here and say Mars. And what do you mean nothing found? Okay, hold on. Oh, I was settings. If we come back into here, to Mars. There we go, Mars. And yeah, I'll bring up my layers, color layers. Just going to turn on a view of Mars that was put together thanks to our Mars reconnaissance orbiters and being at Mars for over 10 years, 50,000 orbits, over 50,000 orbits, contributing to this global mosaic that goes down to 5 meters in resolution. And we can go even higher than that. I'm just going to come in close, like so. And we're reading the global elevation as well. And then finally, let me just come down here and turn on a higher resolution data set for us. And you'll notice tremendous amounts of data in just to even navigate within here. Let's see, I'm going to turn on, that's a better height map. And I'm just going to come down and turn on, great. So what you see is loading, it's jumping around a little bit as we load. This data is located on our server. What surrounds is located on our server in Utah. And then what I'm coming into is another server thanks to our collaboration with Esri. So they also supply us a beautiful Earth image, which is commensurate in many ways to sort of the detail effect that level that you can get with Google Earth. So with this, we actually come down on an image that's 25 centimeters in resolution. A lot of the, I have high school students who actually prepare a lot of the elevation maps from stereo using a free process from NASA Ames Research Center. And but these maps that we're seeing in here were these elevation maps are derived from stereo imagery by the team, Al McEwen, who's a principal investigator, his team at the University of Arizona. Basically, his army of graduate students that come in their first year, they do penance work by actually creating tons of these maps. So That's about what I have to show in open space. I might take a question or two if there's any time left, and but I'll also try to bring up one last thing to show you as far as dynamics of something that we're working on for a presentation tomorrow, in fact. So I'll just minimize this a little and try to bring that up. Oh, Dagstuhl, oh, there were two more things I wanted to show, and so my apologies. Last year, Anders pulled together this team, this group at Dagstuhl in Germany, where we went over what the sort of future of this could be with this interaction and bringing data in. And so I did have a quick little video I would like to show. So if I bring that up and pardon my screen navigation here, it's probably very annoying for all of you. But anyway, let me just come down to this one, turn this on, and I'm going to silence my colleague, Jackie Faherty, good friend. But this illustrates where we're going with this is data interoperability and using this tool called Glue. It's a Python library that actually glues together a lot of different professional astronomical software. So we're looking at a workflow here that Jackie is showing. Let's see. Okay. And she's just selecting the data that, oh, wow. Look at this. I don't want to download it. I want to play it. Let me try it again.
Where OpenSea?
Okay, silencer, and I want to enlarge this. Let me try that again. And so what this enables is astronomers to use the tools they are familiar with. And then that this interoperability with the different tools that they use, we're actually bringing open space as just another tool into this. Okay, it's not playing. My apologies on that. It did. I think I'm stressed on just the amount of internet traffic I can hold right now. So I'll take a question and I'll try to load one of the last things here.
Thank you, Carter, for this very fascinating journey and all the information about this beautiful program. Let's see if there are any questions. If you have a question, please note the button on the bottom of your screen, raise hand, and then I can give you the word. In the meantime, I can probably maybe start with a question of my own. So you are developing all kinds of new materials for open space. What are the main things at the moment that you are working on?
Well, what we are working on right now in the pandemic is actually using open space as a kind of flagship for the museum being closed. So we've been doing these live programs. Let me just see if I can bring this up. Oh boy, I just wanted to. I want to show some. Let me go to my downloads folder. Pardon me for this. And so what we have been working with, let's see. Yes, okay, good. This is what I wanted to show. This is, we've been working with, since the beginning of open space, with NASA Goddard on their Community Coordinated Modeling Center for, I'll just replay this. This is what we're going to be showing live and represents the latest work in open space. We have, and how open space really has been developed by a series of Linköping master's students. So this is their thesis project. In this case, Emily Ho and Christian Adamson have been working as a team to visualize a simulation that NASA has been sort of involved with. But this is actually our National Science Foundation working with modeling the the sun. And I think I have another movie if I just escape out of this for a second. And get out of that. And let me show this other one. Oh boy, okay, yeah, actually this one's good too. Oops, hit the wrong button. And so in this case, Predictive Science Inc. In San Diego has been doing this simulation of how rapidly fast-moving particles come out from a flare to the Earth. That little beacon you see sort of coming from the sun to the Earth illustrates light travel time. And we're looking at a time sped up at 4 minutes per second. And so what you're seeing are this proton intensity over on the right. You're actually seeing the scale bar of essentially a depiction of the radiation and how fast it travels. The highest energy particles are traveling at about half the speed of light. And so if it's 8 minutes from the sun to the Earth, and when you see the sun 8 minutes ago, it's just like, and these particles are traveling at half that speed, and sort of 4 minutes later, we're going to be receiving some of those particles. So in this particular visualization, it's illustrating the nature of open space being able to illustrate you know, these time variant phenomena and really look at these simulations in detail. And so we want that interactivity, both for showing that data. We also want, I'm sorry that the video that I tried to show of the process with glue did not come across too well. But that shows astronomers using tools that they're comfortable using and bringing that data into our digital universe as an overlay, and really looking at filtering the data in glue and seeing instant results in open space. And that can be in a planetarium environment where we had for the Gaia data set, Gaia data set is that Jackie's been focused on that. And we were able to, we had an audience of about 200 scientists that came together for the Center for Computational Astrophysics in New York, which is a new center, new science center. And so we filled the dome with the astronomers. We were looking at this data back and forth. So this is very exciting insofar as the ability to look at that latest science, put it into open space, and that open space can be shown in a flat screen like this, or it can be shown in stereo for VR. It can be shown in a planetarium. So it has this ability to really show a tremendous amount of content, relevant content to scientists, but also the dynamics. Like I just briefly showed a few clips of the material that we're working on for this presentation that we're going to be giving about NASA's work with radiation coming from the sun, and also the concern for how to protect astronauts, because that's a big deal insofar as going beyond the Earth's magnetosphere and getting out out of its protective cover.
Thank you. This is all very interesting and exciting to see. I'm looking forward to it. We also have a few questions, 3 actually. Sure. So, Koen Kuiken, would you like to ask your question?
Sure. Thank you for this very flashy presentation. I was wondering also on time evolution, how feasible is it to, for example, zoom out and then travel in time and watch the Magellanic Clouds go around the galaxy, or watch M30?
Well, if we have a data set for that, that's entirely possible. One data set, it's been embargoed right now, but with the OSIRIS-REx mission, we visualize that. I didn't actually show any of our mission visualizations, such as we visualize missions run by NASA's navigational system called SPICE. Computational system uses their large ephemeris generators, so we know exactly where things are, and so they do for mission planning as well as visualizing the mission after the results come in. But we can show where the camera's looking, and we can actually take the image result and project it to the target. In the case of OSIRIS-REx, we were doing that, and at a conference, we saw that they actually have trajectories for the bits of asteroid Bennu that are falling off, and so we have orbits for all of that. So you have the operations of this mission, OSIRIS-REx, which has gone to asteroid Bennu, and it needs to come in and actually do a sample. It needs to touch down and grab samples. At the same time, it has to figure out where is these potential hazards of this material, which is spinning around this low mass asteroid. So in the same way, for dynamical calculations of Magellanic clouds, we could put that in. If we have that data set, we'd be able to put it in for sure.
Would be cool.
Thank you, Koen. We also have a question from Alexander Shulevsky. Would you like to ask your question?
Yep, thanks, Marlies. Very nice presentation. I had some experience in the past with open space, and I tried to import magnetospheric models of the Earth and also real data measurements from satellite swarms belonging to NASA and ESA. Mm-hmm. And the process was very tedious, and also importing catalogs can be very tedious. And I'm very sorry you didn't manage to show this gluing part of your presentation. Has that advanced? And also, how easy is now to install OpenSpace on Linux? Because that was also, I mean, I managed it, but it required some work. Thanks.
Well, thank you for asking that. So yes, we are multiple operating systems. It's being developed within Windows, so that's sort of your best fit, perhaps. We also have a Mac version, and but generally, it's our developers, which are few, are mastering in Windows, and then also doing a version for Mac. But for Linux, we require that you actually compile it yourself. And so also this difficulty in putting the data in, this is one of the things that does excite us about Glue. Now, what I had intended to show in this video is really an edit down from about a 20-minute video from my colleague Jackie, meant for her students. It was kind of an introduction.
It seems we have an internet problem for a moment.
But it's a sheets on say one plot and see the results in 3D. My internet says it's slow. I'm not sure if I'm speaking too fast or slow. But we also, I should mention, if you download OpenSpace, our website, I didn't even put that up here, but is Open Space Project, one word, openspaceproject.com. We're really a .org, but it's a .com. And there, on that website, we have basically a portal into our wiki and to our GitHub. Also our academic papers, which are really the basis of all of this, and the academic work that, thanks to working with universities, and we're an academic museum as well, is that those papers are all published there. So about like our dynamic scene graph, how we do the atmospheres, the various components of open space, the globe browsing like you're seeing you saw with Mars, are all in there. We have a Slack channel as well, and it's an active Slack channel that our developers are on that. And a number, our user base is growing, but it's not tremendously huge, so it doesn't overwhelm the capabilities of our developers being on that Slack channel to help you out. So that's another important feature I find for users such as yourself that cite, this was difficult to do. We need guidance on this.
Yeah, thank you. Thank you very much.
Sure.
I will definitely check it again because it seems there has been some progress, and I have gotten a message on the chat that actually there is work being going on the data abstraction layer to make it easier to import data. So this is very good.
Great, all right, thank you. So that is the last question for now in view of the time. And thank you again, Carter, for this inspiration.
Well, thank you. And I'm sorry if my style of jumping around is a little crazy, but I did want to just, I'm sorry that the movie about glue didn't quite work, but I think you all get the idea, get the picture of what open space, as Anders pointed out, is such a large concept, but that we want to make it useful for the scientists as well, not just the educational demonstrator. Thank you very much.
Thank you again. We will now go to the last part of this mini conference, and we will go to Edwin Valentijn with the announcement of a new book, the first popular science book on the information universe, Powers of Two. And this will be an expedition through the world and skills of information, resembling the classic powers of 10. So, Edwin, I give the word to you.
Okay. There we are. Thank you very much, Carter. Thank you for your great talk. What we call a tough job to follow. I give myself a little bit much less time. I will be very short and give a little bit a helicopter view of the book we are issuing in the near future. I think your show is really based on open space. It's building computers. It's using computers, and it's using images actually of the two sky, of the two universe. What we do in the computers, I call the information universe in vitro. Some people call it in vivo, in silico. And then there's the crossover to the information universe in vivo, the real physical information universe. And actually, I've always been thrilled about this crossover. And this is also the subject of this conference. And this is also the subject of the book I'm going to present right now. So I'll give you a little bit of a helicopter view of the book. It is co-authored by a large team of speakers and keynote speakers at the Information Universe Conference. I'm very happy they contributed to it. They really helped to broaden the view. And this is really, a product of this community of the information universe. So first of all, I thank all my co-authors for helping and preparing and writing this book. The book is announced by Springer Nature to release in mid-November. The production is a little bit delayed, most likely because of the COVID-19 situation in India. But Springer guarantees me that they give it now high priority and they will have it printed as soon as possible. And as soon as we have it, of course, we will mail it to all the registered guests of the conference. The questions which are addressed in the book are, is there a common denominator that links in vitro to in vivo? Is that information? Is it the building block of everything? Is there a physical difference between in vivo and in vitro? In other words, is our universe one big information processing machine? There are many different approaches to this question, and different speakers have a different view and different approach. But in this book, we follow the powers of two. And it is organized in pads, two-page pads, and each of these pads deals with one of the powers of two. And in this presentation, I'll highlight a few of them, and I will show you a few of them. And clearly, it's not possible to go through all of this, just to give you a little bit helicopter view of what you might expect. It starts a little bit heavy with 2 to the power 0, which is quite mysterious, actually. 2 to the power 0, as you know, is equal to unity. And in the information universe, we identify that with the space-time form, right? The universe, the space-time form out of which our universe has been created during the Big Bang, and in Padnava-Ban's speak during the Big Melt. So in our book, we call that T instead of space-time form. It's actually also taken over by Padnava-Ban to make things a little bit easier to understand, because it's actually a consequence of following the powers of 2. If power to the 1 is a bit, can be identified with a bit. Bit has 2 states. Then we have it from bit, which is the usual statement we make about the information universe, is it from bit. Bit has 2 states. Well, bit should also come from something, bit from T. This is what we present, the way we present it in the book, T being the space-time form. To the power 0, 1 state, the eternal space-time form. And actually this solves a little bit the riddle Charlie Lineweaver also addressed in Iss Trail. It from bit, what is the reverse of it? Where is bit coming from? Well, bit comes from T, the space-time form. That's the approach. And actually that is simply, I didn't even plan to say this or to invent this. It is simple, a consequence if you follow the powers of 2. Then if we carry on with power 2, there's a spread on the multicellular life and how cells started with exchanging information. And cells started exchanging information. Really, one can see that as the moment that real life has started. Then there's the mysterious game of life of John Conway. And I think it's worthwhile to spend some time on that one. The game of life of Conway is well known, it's almost a cult. It only uses a few very simple rules. And by applying these rules in a very simple computer program, which you could already run on the very first MS-DOS computer, you could create creatures and particles and moving things. And here actually we are touching on the basic properties of the information universe, rules as being a building block of the information universe. Rules you can translate also in relations, and you can translate that also into associations. That's a theme which comes back in the book in many different places. Associations as a building block of the information universe. And that's clearly also the case for the game of life. And also I devote this page to John Conway, who unfortunately passed away recently because of complications of the coronavirus. Then I use this spread of 2 to the power 7, which is a spread about ASCII. ASCII is actually a 7-bit string, and it's a table. It's a table of characters, our alphabet, and a bit string. It links the two. It links the characters, and it links the bit string. Actually, it links our computers with our consciousness. We're doing it all the time as we speak, as we type. We're using it all the time without even realizing it anymore. But actually, it is the relation between our consciousness and the computer. Now, what is so strange about it is that this is relation, this is a table, this is an association. And actually, if you think about it, most of our spooky things in our information universe are built out of these, are built on these relations. And this is why the ASCII table is also, I think, a very fundamental thing to understand in information universe. But actually, I wanted to show you this page to show what we do on typical pages. So we have here 7 bits, and 2 to the 7 bits means 128 states, 128 symbols in the alphabet, and 128 different bit strings. On the lower right, you can find links to other pages. And they are addressed here on this page, and you can find links on other pages. Actually, each page you can read in a standalone mode. And by following the links, you can make your own storyline through the book. So in the EPUB version, in the electronic version of the book, you can make your own storylines along the powers of 2. Then just to give you another view of different pages and helicopter view, here is a page devoted to COVID-19, which enters the storyline at 2 to the power 16. And the reason I entered this page is people ask me the question, how can it be that 7.5 kilobyte of information can have such an impact on our society? You know, the RNA virus is only 7.5 kilobytes long. To be precise, it has 30 kilobyte of base pairs, and this 30 kilobyte of base pairs, this 30 kilo base pairs correspond to 7.5 kilobytes of information. How can it be? I mean, 7.5 kilobytes of information is 1/1000th of a second of this Zoom meeting in terms of information which we transfer to each other. How can it be that such a small thing has such an enormous impact? Well, the big trick is actually that the big trick of nature is that this 7.5 kilobytes is glued together in one big string. There's one big address, one big barcode, if you want. And there's so many mutations of this barcode that you can, here's the number, 10 to the power 17,000 different mutations of that string. So you can build much more strings than you can even contain in our universe. You need many universes to even build all the mutations of this virus. Which means that the virus is completely adapted to us. It's completely adapted to our universe. It's completely adapted to the geometry of our universe. It's adapted to our Earth. It's adapted to our atmosphere. It's adapted to our society and to everything we do in life. And that makes it so clever. Because it's highly, highly, highly selected in an incredible way. And this maybe helps to understand why by trial and error and selection of nature, nature creates beasts which are actually a mirror of our own society and our own Earth. All right, well, the same happens actually with DNA, which goes in 2 to the power 32. And Charlie Lineweaver did write a spread on this, actually 3 spreads on this. DNA is, the DNA string has about half a gigabyte of data, which is enormous. And supersedes, of course, the RNA string by a very large factor. Then there's the take by the life sciences with a huge biodatabanks, and the volumes of these databanks belong to the range of 2 to the power 35. An interesting thing there is that these scientists use these databases to discriminate between the role of nature and the role of environment, the role of nature versus nurture. Actually, this is exactly the same question we have in astronomy. This is why I enjoyed it so much to work together with these people, because on a computer science level, we're doing more or less the same thing. They do it with human data and we do it with stars. Okay, then there is a take by the Human Brain Project. Also there we are dealing with extreme numbers. In the human brain, there are about 10 to the power 15 synapses in a single human brain, which is more than there are stars in the largest galaxy we know of. And actually that brings the human brain in the domain of quantum computing, a single human brain. It also supersedes computer AI by enormous factors. And it also consumes so much less energy. The number is 100,000 billion less energy per synapse if you compare to one transistor in computer chips. Also, this page is devoted to a person which is called Hayden Planetarium, who unfortunately deceased shortly after he gave his last talk at the Information Universe conference 2 years ago. Then, of course, there's a take of astronomers who collect big data from the observatories and satellites, such as the Euclid satellite. map here and to map and understand the nature of dark matter and dark energy. And to subsequently ask the question, is it composed of particles and fields or of information? Or is it all information? Such as Erik van Linde has just proposed. And I think this is one of the interesting questions posed in the book. Yeah, I don't think we give all the answers. We give the questions and discuss it together with a number of scientists. And then we observe this stuff. We observe the dark matter. This is, here's a picture of the kids' dark matter maps displayed on top of the stellar sky in the planetarium. You see the Big Dipper here in the middle. And on the other side, you see the black hole image, which you all know about. And there's also a page on the black hole, which is written by Hayden Planetarium. Then I go to the next page, which is about the big data which we are dealing with in astronomy. And astronomy projects really demonstrate the crossover between the big data in our machines and the big data in astronomy, in our universe. And all this transition, this connection, is enabled by spooky links we make. Links is other words for data modeling, metadata, creating links, joins, associations, all different words for the same thing. We make relations and links. The only way we can deal with all the data from the universe is by building that in our computer. And in this context, there are 2 pages, different spreads, one on the universe as a spreadsheet and one on downloading the universe. All right. Then here, there's a spread on 4pi. And yeah, it's not a coincidence that 4pi has been mentioned today in several of the talks, because it plays a key role in the information universe. You could say in layman's speak, if the Hitchhiker's Guide to the Galaxy states that the answer to all the questions is 42, then in the information universe, a lot of the answers to the questions is 4pi. And let me explain that a little bit. Of course, you can find it much more details in the book. But 4pi is the amount of information which is transferred from T, or the space-time form, to in the Big Bang, according to Padnavadan, at the Big Melt. The universe, according to Padnavadan, the universe started with 4pi of information. But 4pi is also the information content of a sphere, this unit radius, and which is corresponding, which is done in the holographic principle. That's a very basic thing. It's a basic thing also for Erik van Linde's theory of dark matter and dark energy. As a matter of fact, it's also the basic thing for the derivation of black body radiation, which is considered as one of the 3 big inventions in the last century, next to quantum mechanics and general relativity. Also, black body radiation is a 4pi thing. Strange enough, the International Weather Observatory, which connects over 2,000, perhaps it's already 3,000 different databases all over the world, which everybody can use seamlessly and get information on the sky wherever it is. Actually, the whole Vitro observatory is enabled by recognizing 4pi and pixelating the 4pi surface and having all the databases recognizing these pixels on the 4pi surface. So 4pi is actually the geometry of our universe, and it's more or less also us. And this is also one of the topics which Robert Dijkgraaf touched in his foreword. This is really the 21st century metaphor. Not necessarily the ultimate theory, we don't have that theory yet, and but we all work on it. Okay, well, in these days you also have to, this internet and fake news, we all know what this is about. We also have to review facts and fakes, and there are some spreads dedicated to this, because it really forces us to review and revisit the system of science and how we determine something to be true or not to be true. What is really the process, how we do that. And then I close this with the Spider Live. I didn't expect that the last page of the book would be about life. I thought it would be about the big numbers in the universe. But actually, I already revealed that the number of mutations you have in DNA is so incredibly large that you need an unmeasurable amount of universes to get all the different mutations of DNA. Actually, in other words, life is so much more complex than we meet in our astronomical observations. This is remarkable. I find it remarkable. Of course, there will be many people who already knew this. The biologists knew this. The DNA people knew this. But this is rather a remarkable thing. And I find it an interesting conclusion. And it also has some impact on our evaluation of the question, how much life is there in the universe? I personally think if you realize this number, then it really doesn't make sense to count the number of planets to evaluate what is the chance to find other intelligent life in the universe. So yeah, that's one of the main conclusions of the book. And I think I close my presentation here. I have to want it to be short. I hope I was short. Then I will show you a little trailer which has just been produced, and this is going to be on the next page. Here it comes. As a small kid, I used to take long walks after dinner with my philosophical father, and we would watch the stars in the pitch black dark skies. I was intrigued by the two big questions. What is out there? Where do we come from?
The book, Powers of Two, addresses these big questions. Is everything around us information? Does it come from bit? In this book, we experience how information lies at the very foundation of our understanding of the universe.
Everything I do, I considered as a laboratory to understand the role of information in nature. And this is exactly what we are doing here, also in this theater.
What is the universe? Is the universe one big information processing machine? The Powers of Two travels from small to bigger and bigger amounts of information, from the creation of the very first bit at the Big Bang, via the evolution of life, through 50 years of computational science, and finally into deep space, where we meet information at the 4π surfaces of black holes, and filling the universe in the cosmic microwave background, and even perhaps in the dark energy. But, according to Padmanabhan, the universe did not start with a Big Bang, but with the Big Melt, transferring 4π of information. Powers of Two addresses these questions through the collaboration of different world-class scientists. Let them guide you through all the different flavors of the information universe.
Your body contains information. That information came from the universe. All of the letters behind me, ACGT, ACGT, there are 3 billion letters like that inside of your cells. And that's the information that made you.
There are 1,000 trillion synapses in the human brain, which brings it to the domain of exascale computing. Yet it consumes less energy than a light bulb. To simulate a brain on a computer requires much more energy. Can we learn from the brain?
But how did the universe get information in the first place? Where did that come from?
So one of the beautiful things we start to realize over the past few years is that all these results that we see behind us that come from physics and mathematics over the last 300 years, that there is a thing that is coming short there, and that is a deeper understanding of how things are connected together, how the complexity evolves over time, how life actually emerges. And that's what information science might provide us with.
to understand my theory of emergent gravity, you have to look also at how the language of science has been changing over the centuries. We live in an information age.
What does this book mean to me? Powers of Two is a trip to our world, to our lives and our universe. It addresses the big questions of today. Thank you so much. This closes this part of my presentation. And what I will do now is I will remove my virtual background and go down to Earth. And I'm back in my office at home, like most of us are. And I will start the last 5 minutes of the program. And the last 5 minutes of the program is really thanking the different people. But let me first do something else and show you that the book is really existing. And here it is. This is the very first copy. The ink is still fresh. And I'm really pleased to show this first copy and to show you a few of the pages. This is quite an exercise to do this in front of my computer. There you go. So it's there. It's in production now, and it's a few hundred pages, and it touches a lot of subjects on our universe. And I hope you will enjoy it. Then, from the last 5 minutes here, I will thank all the different contributors to this conference and also to the book. Actually, there's a little bit of overlap. Let me first thank the people who helped to make this conference possible. First of all the speakers this afternoon. Second, all the chairmen and the co-chairs. Thank you for doing this. I think I enjoyed it very much, and it was relatively successful. No big hiccups. It's quite an exercise for us. The first time we did it. And the person behind the screens we did all this was Rhys Williams, the chair of our local organizing committee. Thank you, Rhys. You did a really fantastic, marvelous job. I know what it took. And so it really went very smooth. Thank you very much, Rhys, for doing all this. And also thanking the scientific organizing committee for making the program and the local organizing committee. Then I also want to thank the people who helped to make this book possible. I want to close with that. First of all, I have to mention Angela Lahi, the executive editor of Springer Nature. She was really very persistent. She really helped me because I was always, as usual, a little bit a difficult guy who had his own design and his own format and his own way of doing things. And a book which is, on the one hand, a conference proceeding, and on the other hand, a popular science book, never been done before. So it was all a little bit different. And she really helped me helped very much to get this through the Springer production. And I'm very grateful to her. I really also thank the ladies, and you can see them on top of the screen, on the gallery mode. I thank you, Anne. Hello, Anne. Are you there? Yeah, you're there. Thank you very much for assisting us with the editing. Then Madalena, you're there. Say hi. If you're hi, you get in speaker's mode, but you're muted.
Hello.
If you have to say hi, we can all see you. Okay, fantastic. Thank you very much, Madalena. And then there's Josje from Studio Frontaal. And also say hi. I hope you get in the speaker's mode. No, you're not in speaker's mode. Okay, but anyway, thank you very much, Josje. You made a big difference. You brought the design to another level. And I have the book in my hands, and I'm really extremely amazed about the result. Thank you so much.
You're very welcome.
Hey, there she is. Now she's talking. Now I see you on the screen. On my home screen, I see you. But thank you very much, Josh.
Yes.
And last but not least is Margot. And but then there's always this little thing, you know, if there is a book, you have to, here is the book, ladies and gentlemen. And normally if there's a new book, you have to hand it over to someone. And well, it's all very difficult to do this virtually, but I decided to hand it over to Margot. Because she did this fantastic work as a assistant editor. She did more than normal as an assistant editor. She wrote a couple of chapters, and she also edited quite a number of chapters with our co-authors, and did a lot of work making it consistent. She's master of consistency, so if things are consistent, then it's because of Margot. Thank you very much, Margot, and therefore I hand over here now the first copy of the book virtually. Get it? Yeah, you got it. Yeah, you got it. Thank you so much. You're going to make a travel. Well, you had to cancel your travel to New Zealand. I'm very sorry for you and Jasper, but there will be times that you can make your travel, your big trip, and I'm sure you will get there sooner or later. Okay, ladies and gentlemen, I think this is it as far as this meeting is concerned. I don't think there's any more questions, and I really want to thank you all for attending and for being there. And I hope